Gas-insulated lines (GIL) are a sophisticated and efficient solution for the transmission of high-voltage electricity. These lines are composed of a central aluminum conductor that is surrounded by an insulating gas mixture, typically composed of nitrogen N2 and sulfur hexafluoride SF6, all housed within a robust aluminum tube. This unique design allows GILs to efficiently transport electricity over long distances with minimal electrical losses and reduced electromagnetic field emissions. The insulating gas mixture enhances the dielectric properties of the line, ensuring that the system remains reliable even under high-voltage conditions. One of the standout advantages of GILs is their ability to operate safely in various environments. The use of SF6 gas, despite its high global warming potential, is tightly regulated and contained within the system, preventing any leakage. This makes GILs a safer and more environmentally friendly alternative compared to traditional methods. Additionally, the fire-resistant properties of the aluminum tube and insulating gas mixture provide an added layer of safety, making GILs suitable for areas with strict fire safety regulations. GILs are particularly useful in densely populated urban areas, tunnels, and regions where overhead power lines are not feasible due to space constraints or aesthetic considerations. Their compact design and minimal visual impact make them an attractive option for city planners and engineers. Furthermore, GILs can be installed underground or within existing infrastructure, reducing the need for extensive and disruptive construction projects. In terms of performance, GILs offer several benefits over traditional overhead lines and underground cables. The aluminum conductor's low resistance and the insulating gas's high dielectric strength result in lower transmission losses and higher overall efficiency. This makes GILs an ideal choice for long-distance power transmission, where energy losses can be a significant concern. Additionally, the reduced electromagnetic field emissions help mitigate potential health risks and interference with nearby electronic devices. Overall, gas-insulated lines represent a cutting-edge solution for modern power transmission needs. Their advanced design, combined with their safety and efficiency advantages, make them a reliable and sustainable option for transporting high-voltage electricity in various challenging environments. As the demand for electricity continues to grow, GILs will likely play an increasingly important role in ensuring a stable and efficient power supply. Gas-insulated transmission lines have several advantages, but they also come with notable disadvantages that need to be carefully considered, especially in comparison to traditional transmission methods. One of the primary disadvantages of GIL is the high initial cost. The installation of GIL systems requires significant upfront capital investment due to the cost of materials such as SF6 gas, metal enclosures, and the specialized techniques needed for installation. This makes GIL systems significantly more expensive than overhead transmission lines, particularly in long-distance applications. Additionally, the environmental impact of SF6 gas is a major concern. SF6 is a potent greenhouse gas with a global warming potential GWP that is 23,500 times greater than CO2. Although leakages are rare, even small emissions of SF6 can have severe long-term environmental consequences, which puts pressure on system operators to minimize and manage gas emissions effectively. Another challenge with GIL is its complex installation process. Installing GIL, particularly in underground configurations or tunnels, requires specialized techniques and machinery. This not only increases the complexity of the project but also extends the installation time and results in higher labor costs compared to overhead lines. Furthermore, once GIL systems are installed, modifying or expanding the network can be difficult. Underground or tunnel installations limit accessibility, making it harder to change the layout or upgrade the system to meet future power demands. This limited flexibility can hinder GIL's adaptability in dynamic power grid environments. Maintenance challenges also arise with GIL systems. Although GIL requires less routine maintenance compared to overhead lines, the enclosed and underground design makes it more difficult to perform inspections and repairs when issues occur. For example, systems buried underground or located in tunnels are harder to access, requiring specialized equipment and personnel for maintenance work. The installation of expansion joints to accommodate thermal expansion and contraction further adds to the complexity of the system, requiring additional space and increasing design challenges, especially in long-distance installations. Operational flexibility is another limitation of GIL. Once installed, the system has a fixed configuration, and rerouting the transmission path or modifying the system in response to infrastructure changes such as new buildings or roads is complex and expensive. Additionally, SF6 handling and management add another layer of complexity. The gas must be handled carefully to prevent leaks, and skilled personnel are required for regular gas monitoring, maintenance, and potential refilling. This further increases the operational costs of maintaining a GIL system. The long installation time is another drawback, as it often takes longer to install GIL compared to overhead lines, especially in tunnel or underground configurations. This can delay project timelines and increase costs due to prolonged labor. Furthermore, aging is an issue with GIL systems. Over time, the insulating properties of SF6 gas can deteriorate, particularly if it becomes contaminated by moisture or impurities. This can reduce the reliability of the system and necessitate regular monitoring and gas refilling to maintain the required insulation levels. GIL systems also present inspection challenges. Periodic inspections are harder to perform due to the system's underground or tunnel placement, making visual assessments difficult and requiring specialized equipment for condition monitoring. Additionally, GIL's routing flexibility is limited once installed. If infrastructure changes occur, such as new road construction or urban development, it can become difficult to reroute or access the system for repairs. Lastly, GIL systems face heat dissipation challenges. Although designed for efficient heat management, densely packed installations such as in tunnels can face difficulties in dissipating heat effectively. This can lead to reduced performance or necessitate additional cooling solutions. Moreover, due to the environmental impact of SF6, the cost of recycling or disposing of the gas at the end of the system's operational life can be high. Strict environmental regulations surrounding SF6 handling mean that end-of-life recycling or disposal requires specialized procedures, further increasing the overall cost of operating a GIL system. One of the critical factors is the long-term maintenance and monitoring required for SF6 gas. While SF6 is highly effective as an insulating medium, its performance can degrade over time due to factors such as contamination, moisture, or leaks. This necessitates continuous monitoring of gas pressure and quality to ensure the integrity of the insulation. Failure to maintain proper gas levels can lead to system failures, electrical breakdowns, or reduced operational efficiency. Specialized equipment is often required for gas analysis and leakage detection, adding to the operational costs. Furthermore, the installation environment plays a significant role in GIL's overall performance. GIL systems installed in tunnels or underground can face issues related to environmental conditions, such as moisture, soil movement, and potential exposure to corrosive elements.